What if the universe has already shown us something impossible, and we've been staring right at it all along? Tonight, we journey to the edge of what science can explain, where the laws of physics begin to blur. Welcome to Cosmic Drift. A flashlight is switched on inside a spacecraft moving past Earth. The ship is already crossing space at half the speed of light. Its nose points forward. The beam leaves the lamp in the same direction. Ordinary motion gives an obvious prediction. Throw a ball from a moving train, and the speed of the train is added to the speed of the ball. Fire the flashlight from a fast enough ship, and the beam should race ahead faster than light from a lamp on Earth. A ship chasing the beam should measure it moving more slowly. A ship flying toward it should measure it moving more quickly. None of that happens. The crew measures the light, leaving at exactly the speed of light. Observers on Earth measure the same beam at exactly the speed of light. Another spacecraft rushing toward the beam measures exactly the same speed. Change the motion of the lamp. Change the motion of the observer. Change the color, energy, or direction of the light. In empty space, the answer refuses to change. The familiar number is 299,792,458 meters per second. Today, that value is exact because humanity defines the meter through it, but the definition is not the explanation. It is a sign of how completely this number has taken control of measurement. We no longer use a ruler to find the speed of light. We use the speed of light to tell us what a ruler is. That still leaves the real question untouched. Where does this speed come from? A photon does not carry a tiny engine. A brighter lamp does not launch faster light. A hotter star does not push its photons harder. Gamma rays, visible light, radio waves, and the faintest microwave crossing intergalactic space all share the same vacuum speed. Light does not accelerate up to that value after being created. In the theory that describes it, light begins on that boundary and never leaves it. The first answer sounds almost like a reversal. The speed of light is not mainly a property of light. It is a property of the structure through which every cause, signal, and physical influence must travel. Light reveals that structure because light has no rest mass. It is forced to move along the boundary that separates events that can affect one another from events that cannot. That boundary is why a moving observer cannot catch the beam and make it crawl. Instead, measurements of distance, duration, and simultaneity rearrange themselves so that the boundary remains fixed. Time changes before the speed of light does. Space changes before the speed of light does. Even the meaning of now changes first. If watching a familiar number turn into the architecture of reality is the kind of journey you want more of, subscribing is a small way to help me make the next documentary. Because the next step is to watch humanity discover that light was not instantaneous at all. For most of history, that was not obvious. Light seemed to arrive without delay. Open a door at noon, and the room brightens at once. Look toward a mountain, and there is no visible pause between the sunlight touching its slope and the image reaching the eye. Even across the distances available on Earth, light moves so quickly that ordinary senses have no chance of separating departure from arrival. Galileo tried anyway. In the early 17th century, He described an experiment involving two observers on distant hills, each holding a covered lantern. One observer would uncover a light. The second would uncover another as soon as the first became visible. If the first observer measured a delay greater than human reaction time, perhaps that delay would reveal how long light needed to cross the gap. The experiment could not work at that scale. Light can cross 10 kilometers in a tiny fraction of the time required for a person to see a flash and move a cover. The method was not foolish. The world available to it was simply too small. The successful clock was not built on Earth. It was already orbiting Jupiter. In 1676, the Danish astronomer Ole Rømer was studying Io, the innermost of Jupiter's 4 large moons. Io circles Jupiter in less than 2 days. On each orbit, it enters Jupiter's shadow and disappears, then later emerges. Those repeated eclipses behave like the ticks of a remote clock. If light crossed space instantly, the clock should keep the same apparent schedule no matter where Earth happened to be in its orbit around the Sun. But Earth does not remain at one distance from Jupiter. Over part of the year, the two planets move generally closer. Over another part, Earth moves farther away. The change adds or removes a distance comparable to the width of Earth's orbit. Rømer noticed that Io's eclipses seemed to arrive progressively early while Earth approached Jupiter, and progressively late while Earth moved away. The moon itself was not repeatedly speeding up and slowing down in step with Earth's location. The cleaner explanation was that the news of each eclipse needed time to cross the changing distance. When Earth was farther away, the news arrived later. This was a profound kind of measurement. Rømer had no switch he could press on Jupiter. He did not know the modern value of the astronomical unit with enough precision to calculate today's exact speed. He was using an orbit as a signal, another orbit as a moving baseline, and the solar system as an apparatus too large to build. The result transformed darkness between the planets. Empty space was no longer a place across which vision happened instantly. It was a distance that information had to cross. Christian Huygens soon combined Rømer's delay with an estimate of the size of Earth's orbit and produced a numerical speed. The estimate was rough because the scale of the solar system was still rough, but the essential result survived every improvement. Light was extraordinarily fast and unmistakably finite. That distinction matters more than it first appears. An infinite speed would erase travel time. Every point in the universe could respond to every other point without delay. A finite speed gives the universe causal depth. The sun can change before Earth knows it. A star can die while its older light is still approaching us. Distance becomes history. Rømer's method also exposed a pattern that will return throughout this story. The speed of light does not announce itself through the motion of a glowing object. It appears through timing. A moon goes dark. A signal arrives late. Two clocks disagree. The structure is found in the delay. Astronomers improved the value by watching other celestial effects. James Bradley used the aberration of starlight, a slight annual change in the apparent direction of stars caused by Earth's motion and the finite speed of light. The effect is sometimes compared with tilting an umbrella while walking through vertical rain. The rain is not really slanting in the ground's frame, but the combination of its fall and the walk changes the direction from which it seems to arrive. The analogy helps with the geometry, but light would soon punish anyone who pushed the comparison too far. Rain has a preferred frame in the air. Light does not behave as though space supplies an equivalent wind. Before that contradiction could become unavoidable, physicists first had to bring the measurement indoors. By the middle of the 19th century, the target was no longer merely to prove that light had a finite speed. The challenge was to measure a journey so short that it could be controlled on Earth. In 1849, Hippolyte Fizeau sent light through the gap between teeth on a rapidly rotating wheel. The beam traveled to a distant mirror several kilometers away and returned toward the same wheel. At a low rotation rate, the returning beam passed back through the gap. At a carefully chosen faster rate, a tooth moved into the returning beam's path and blocked it. The machine turned time into geometry. Fizeau knew the distance to the mirror. He knew the spacing of the teeth. He knew how rapidly the wheel had to rotate before the returning flash was extinguished. From those pieces, he could infer how long the round trip had taken. His result was about 313,300 kilometers per second. It was too high by modern standards, but it was close enough to be astonishing. Light had crossed kilometers of countryside, struck a mirror, returned, and met the next tooth of a wheel at exactly the predicted moment. A few years later, Léon Foucault replaced the toothed wheel with a rotating mirror. The tiny change in the mirror's angle during the beam's travel shifted the returning light. Measuring that shift improved the result dramatically. By 1862, Foucault obtained a value close to 299,800 kilometers per second. The cosmic delay had become a laboratory interval. Yet the improving number created a deeper problem. Measuring how fast light moved did not explain what was moving, what carried the wave, or why the value appeared to be linked to electricity and magnetism. The decisive clue would come from equations that were not written to solve the speed of light at all. In the 1860s, electricity and magnetism still looked like related but partly separate kingdoms. Electric charges could attract or repel. Electric currents could produce magnetic effects. Changing magnetism could drive electric current through a wire. Experiments had revealed the links, but the pieces had not yet become one moving system. James Clerk Maxwell found the missing motion. Imagine two metal plates facing one another, with empty space between them. Connect the plates to a source of current, and charge begins to accumulate. Current flows in the wire, yet no charge jumps across the empty gap. If magnetism were created only by charges physically crossing a surface, the magnetic description would break at the gap. Maxwell repaired the break by treating a changing electric field as something that could play the same role as current in the magnetic equations. The change was not a convenient patch. It allowed electric and magnetic fields to sustain one another in open space. A changing electric field creates a changing magnetic field. A changing magnetic field creates a changing electric field. Once disturbed, the coupled fields can carry that disturbance away. The result is a wave. The equations also say how quickly the wave travels. The speed depends on the electric and magnetic response built into the equations for empty space. When Maxwell compared the predicted wave speed with the measured speed of light, the values matched. That was the collision. Light had entered the story as vision, reflection, color, and rays. Electricity had entered through sparks, charges, batteries, and wires. Magnetism had entered through lodestones and compass needles. Maxwell's equations said these were not neighboring subjects. Light itself was an electromagnetic wave. A radio signal, a warm infrared glow, visible green light, an ultraviolet photon, an X-ray, and a gamma ray differ in frequency and wavelength. They are different movements of the same electromagnetic field. In vacuum, the product of frequency and wavelength always produces the same propagation speed. Raise the frequency and the wavelength shortens. Lower the frequency and the wavelength lengthens. The speed does not need to follow either one. This is the first major answer to where the speed comes from. Classical electromagnetism contains a wave speed in its own structure. The value was not attached afterward, because experiments said light was fast. Solve the equations in empty space, and a fixed speed appears. But that answer has a limit. Older descriptions often say the speed is set by two properties of the vacuum, called electric permittivity and magnetic permeability. That language can sound as though empty space were a hidden material with electrical stiffness and magnetic inertia, like a springy substance that determines how fast a ripple can move through it. Historically, the measured constants did help reveal the electromagnetic wave speed. In the modern system of units, however, the speed of light is fixed exactly, and one of those electromagnetic constants is measured rather than defined. The equation still works. The bookkeeping has changed. More importantly, Maxwell's theory tells us that electromagnetic disturbances propagate at a particular speed. It does not by itself explain why every freely moving observer must obtain that same speed. Under the ordinary rules of motion, an observer chasing the wave should still subtract their own velocity. That is what happens with sound. A sound wave moves through air. Walk toward the oncoming wave, and the wave fronts reach you more rapidly. Fly with the wave, and they reach you more slowly. The speed of sound has meaning relative to the air, because the air is the material whose pressure and density carry the disturbance. 19th century physicists therefore expected light to have a carrier as well. They called it the luminiferous ether. It had to fill apparently empty space. It had to pass through ordinary matter or surround it without obvious drag. It had to support transverse waves, which suggested rigidity. Yet planets had to move through it with almost no resistance. The ether needed to be more rigid than steel for the purpose of transmitting light, and more elusive than the best vacuum for the purpose of letting worlds pass. That strange collection of demands was not enough to kill the idea. Waves had always belonged to something. Water waves belonged to water. Sound belonged to matter. A light wave without a medium seemed incomplete. If the ether existed, it also offered an answer to the observer problem. Maxwell's wave speed would be measured relative to the ether. An observer at rest in that medium would obtain the true value. Everyone else would measure a slightly different value depending on motion through the ether. Earth could not remain at rest in it all year. Our planet circles the sun at roughly 30 kilometers per second. Even if the solar system happened to be motionless relative to the ether at one moment, Earth's orbital direction changes over the year. At some point, a laboratory should be moving through the medium. The expected effect was an ether wind. Think of a boat crossing a river. If it travels upstream and then downstream, the current changes the round-trip time. If it crosses the river sideways and returns, it must aim partly into the flow to avoid drifting. The two round trips are not identical. Rotate the routes, and the timing difference follows the current. Albert Michelson designed an instrument that translated this expected timing difference into an interference pattern. A beam of light was split into two paths at right angles. Mirrors returned the beams so they could be recombined. Light is a wave, so the peaks and troughs of the returning waves either reinforce or cancel one another. A tiny difference in travel time shifts the bright and dark interference fringes. One arm would briefly lie more nearly along Earth's motion through the ether. The other would lie across it. Rotate the entire instrument, and the roles would exchange. If the ether wind existed at the expected strength, the fringes should slide. Michelson's first attempt did not reveal the expected shift. In 1887, he and Edward Morley built a more sensitive version. The light was reflected back and forth to increase the effective path. The heavy apparatus floated on mercury so it could rotate smoothly. Stone walls and careful temperature control reduced disturbances. Again, the large predicted shift failed to appear. The experiment is often reduced to a single dramatic sentence. Michelson and Morley proved that the ether did not exist. History was less tidy. Their result constrained a particular expected motion through the ether. Some physicists modified ether models rather than abandoning them. George Fitzgerald and Hendrik Lorentz proposed that motion through the ether might physically contract the arm aligned with the motion, exactly enough to hide the timing difference. Lorentz developed transformations that made Maxwell's equations keep their form between moving systems. The rescue worked mathematically. It also made the medium increasingly impossible to expose. The ether caused objects to contract, clocks to change, and experiments to conceal the laboratory's motion through it. A substance invented to provide a preferred state of rest had become a substance whose preferred state could not be found. Michelson and Morley did something more important than fail to detect a wind. They sharpened the contradiction between two successful pictures of nature. Newtonian mechanics said velocities add. Maxwell's electromagnetism carried a fixed wave speed. Experiments refused to reveal the frame in which that speed belonged. One could save the old picture by adding compensating changes to matter moving through the ether. Or, one could ask whether the old picture of space and time was the part that had failed. That second move is what made the speed of light stop being only a property of electromagnetism. In 1905, Albert Einstein began not with a mechanism hiding inside empty space, but with two rules about what any freely moving observer is allowed to call physics. The first rule said that the laws of physics take the same form in every inertial frame. An inertial frame is simply a viewpoint moving steadily without acceleration far enough from complications that no local experiment reveals a special state of uniform motion. A sealed laboratory, gliding smoothly through deep space, should not contain a device that tells its occupants they possess the universe's true rest frame. The second rule said that light in empty space is propagated with a definite speed, independent of the motion of the source. Put those rules together, and ordinary ideas of space and time cannot survive unchanged. Return to the spacecraft and its flashlight. Suppose the ship passes Earth at a large fraction of the speed of light. At the instant it crosses a marker, the crew sends a pulse toward the front of the cabin. An observer on Earth sees the ship moving, while the light crosses it. The front wall is running away from the pulse, so from Earth's viewpoint, the light must travel farther than the length of the cabin before it arrives. The crew does not agree that the cabin is running away from its own light. For them, the front wall is at rest. The pulse crosses the ordinary cabin length. Both observers measure the pulse at the same speed. They cannot therefore agree about both the distance traveled and the time taken. This is not an error in either clock. It is the price of keeping the laws of physics identical in both laboratories. A light clock makes the price visible. Place one mirror on the floor and another directly above it. Let a pulse bounce between them. Each round trip is a tick. Inside the spacecraft, the light travels straight up and down. From Earth, the entire clock moves sideways, so the pulse follows a longer diagonal path between the same two ticks. Earth's observer still measures the pulse moving at the speed of light. A longer path at the same speed requires more time. The moving clock ticks more slowly. That conclusion cannot be confined to the mirrors. The crew could compare the light clock with a mechanical watch, a vibrating atom, a chemical reaction, a heartbeat, or the decay of an unstable particle. If one kind of clock slowed while another did not, the mismatch would reveal absolute motion. The relativity principle forbids that. Every physical process inside the moving system must share the same change. Time dilation is not a defect in a particular clock. It is a relationship between paths through space-time. From the crew's viewpoint, Earth is moving, and Earth's clocks run slowly. That symmetry sounds contradictory only if everyone shares one universal present. They do not. To see why, imagine a long train moving past a platform. Lightning strikes the front and rear of the train. An observer standing at the midpoint of the platform receives both flashes together and concludes that the strikes occurred at the same time in the platform frame. The midpoint passenger is moving toward the flash from the front and away from the flash from the rear. Because both flashes still travel at the same speed relative to the passenger receives the front flash first. After accounting for position and motion, the passenger concludes that the front strike occurred before the rear strike in the train frame. This is not the simple delay caused by light taking time to reach different places. Each observer corrects for that delay using the same light speed. The disagreement remains. Events that are simultaneous in one moving frame need not be simultaneous in another. The universe gives up a universal now before it gives up the invariant speed. That is the deeper adjustment. Space and time are not separate stages on which motion happens. They are parts of one geometry, and different observers divide that geometry into space and time differently. A distance for one can contain part of a time interval for another. A time interval for one can contain part of a distance for another. The speed of light is the conversion that holds the geometry together. A second can be treated as a certain amount of time, or multiplied by the invariant speed, and treated as a distance of almost 300,000 kilometers. This does not mean time is secretly measured in kilometers. It means the geometry has a fixed relationship between its temporal and spatial directions, much as a map needs a scale to compare a centimeter on paper with a kilometer on the ground. The map analogy has a limit. Space and time do not combine with the ordinary distance rule of a flat sheet of paper. In space-time, the temporal part enters the interval differently from the spatial parts. That difference creates light cones and distinguishes possible causal motion from impossible causal motion. For now, the practical consequence is enough. When two observers move relative to one another, they disagree about lengths, durations, and simultaneity in exactly the coordinated way required to preserve the same space-time interval and the same invariant speed. A moving object is shortened along the direction of motion when its length is measured within another frame. Again, this is not a visual illusion. Measuring length requires recording the positions of the front and rear at the same time. Since different frames disagree about which separated events are simultaneous, they can disagree about the measured length without either one being mistaken. Time dilation, length contraction, and the relativity of simultaneity are not three independent tricks added to save the speed of light. They are different faces of the same geometry. Now ask the question that makes the result feel impossible. What if the spacecraft simply goes faster and faster until it nearly catches the beam? At half the speed of light, ordinary subtraction predicts the beam should pull away at half the speed of light. At 99% of the speed of light, ordinary subtraction predicts only a thin remaining difference. But relativistic velocities do not add and subtract that way. The moving ship's meters and seconds are related to Earth's meters and seconds through the Lorentz transformation. When the crew divides the distance the light covers by the time on their clocks, the transformations cancel in exactly the way needed to return the same speed. The ship can reduce the relative speed of almost any massive object. It can pull alongside another craft. It can overtake a particle moving more slowly. It can never enter a frame in which a vacuum light pulse is at rest. There is no valid rest frame for a photon. This point prevents one of the most seductive mistakes in popular explanations. It is often said that no time passes for light, or that a photon sees the entire universe collapsed into one instant. But seeing and experiencing require a physical reference frame. The mathematics of special relativity does not permit an inertial frame moving at the speed of light. The proper time along a light-like path is 0, but that does not create a photon's viewpoint. It marks the boundary where the notion of a massive observer's clock no longer applies. The closer a massive spacecraft moves to the speed of light, the more energy is required for each additional increase. Its speed can approach the boundary without reaching it. The energy required to reach the boundary grows without limit. Nothing special happens because an engine becomes weak at that point. The obstacle is geometric. A massive object follows a time-like path inside the light cone. Reaching the speed of light would require that path to become light-like. No finite push can change a massive world line into the path of a massless excitation. This also explains why light does not need to accelerate from rest. A photon is not a tiny, massive pellet fired so violently that it reaches the maximum speed. In the quantum description, it is an excitation of the electromagnetic field with zero rest mass. A free, massless excitation cannot sit still. It cannot choose a slower inertial speed. Its allowed path in vacuum lies on the light cone. Higher energy changes a photon's frequency and momentum, not its vacuum speed. A red photon and a gamma ray carry very different energies. Both move along the same causal boundary. The phrase speed of light therefore places the emphasis backward. Light is one of the things that moves at the invariant speed because light is massless. If another massless influence exists and obeys the same space-time symmetry, it must share the boundary. Gravitational waves provide a spectacular example. They are ripples in space-time geometry rather than electromagnetic waves. They do not consist of photons. Yet general relativity predicts that they propagate locally at the same invariant speed. The boundary is not owned by light. It is the maximum speed at which a cause can become an effect. Take any event and mark it as a point in space-time. A lamp flashes. A particle collides. A radio transmitter changes its signal. From that event, light can spread outward in every direction. As time passes, the expanding sphere of possible light positions traces a cone through space-time. Events inside the future cone can be reached by something moving slower than light. Events on the surface can be reached by light or another massless influence. Events outside lie too far away for any signal moving at or below the invariant speed to arrive in time. The past cone contains events that could have influenced the original event. The region outside both cones contains events separated in a way that makes their time order depend on the observer. That last sentence is where faster than light travel becomes more dangerous than a mere speed record. Suppose two spacecraft move relative to one another. One sends a hypothetical faster than light message to the other. Because the message connects events outside an ordinary light cone, there are valid frames in which the receiving event occurs before the sending event. That does not yet produce a contradiction by itself. The order of space-like separated events is allowed to differ. Now let the second craft immediately return a faster-than-light reply using the same kind of rule in its own frame. With a suitable relative motion and sufficiently fast signals, the reply can reach the first craft before the first message was sent. The sender could receive a warning that says "Do not transmit," then obey it. The return message exists only if the original message does, while the original is cancelled because the return arrived. The problem is not that physicists dislike surprising travel. The problem is that controllable faster-than-light signaling allows causal loops unless some additional preferred frame or new rule prevents them. Special relativity protects cause before effect by making the light cone a boundary. This is why the invariant speed is more fundamental than the name attached to it. Even a universe with no eyes and no visible light would still need a causal structure. its fields could possess massless disturbances that mark the same cones. The constant would remain in the geometry even if no creature called the messenger light. Physicists often write equations in units where the speed of light is set equal to 1. This does not mean the physical limit has vanished. It means distance and time are being expressed in compatible units, so the conversion factor no longer clutters every line. A year can be paired with a light year. In those units, saying that a signal moves at 1 means that it covers 1 light year in 1 year. The number 299,792,458 belongs partly to human choices about meters and seconds. Change the units, and the number changes. Use kilometers and seconds, and it becomes roughly 300,000. Use light years, and it becomes 1. What does not change is the physical statement that every local inertial observer finds the same finite causal speed, and that massive objects remain below it. This distinction answers one version of the question and exposes another. Asking why the speed has that decimal value is largely asking why humanity chose those units. Asking why space-time contains a finite invariant speed at all is asking about the architecture of the universe. Special relativity accepts that architecture as a principle. Maxwell's theory reveals that electromagnetic waves respect it. Quantum field theory builds the same symmetry into the fields that fill space. None of those steps derives the existence of Lorentzian spacetime from something universally accepted as deeper. There are proposals in which spacetime and its symmetries emerge from more fundamental physics. There are searches for tiny violations at extreme energy or distance. So far, Lorentz symmetry has survived. Modern descendants of the Michelson and Morley experiment compare light resonating in cavities pointed in different directions. If the maximum speed varied with direction as Earth rotated, the resonance frequencies would drift in a repeating pattern. Experiments have constrained such anisotropy to astonishing precision, reaching fractional levels around 1 part in 100 quadrillion in carefully controlled laboratory tests. Nature has not merely hidden an ether wind from 19th century equipment. Across vastly improved experiments, the symmetry remains. The quantum description deepens the result without turning it into a mechanical story. An electromagnetic field exists throughout space. Its possible states are quantized, meaning exchanges of energy occur in discrete packets. A photon is one quantum of that field. It is not a bead traveling inside a separate wave, and the wave is not a trail pushed through an invisible substance. The field and its quantum excitation are parts of the same description. The field has a symmetry that leaves the photon massless in the standard model. Saying massless is not only saying very light. It means the energy and momentum relation lacks a rest mass term. For such an excitation, the geometry permits only light-like propagation in vacuum. Experiments continue to test whether the photon might possess an extraordinarily tiny mass. A non-zero mass would change electromagnetism over long distances and could make different frequencies propagate differently in vacuum. Observations are consistent with zero. The working theory therefore treats the photon as exactly massless. Even this does not give a final reason for why the electromagnetic field has that symmetry, or why the universe chose this set of fields. It tells us what follows once the structure is present. That is an important kind of scientific answer. Physics often does not explain a fact by finding gears beneath it. Sometimes it discovers that the fact is a consequence of a symmetry, and the symmetry is woven through every successful equation we have. The speed of light does not come from fuel, it comes from permission. Space-time permits massless disturbances to move on its causal boundary and permits massive objects to move inside it. The electromagnetic field supplies a massless disturbance. Light follows the route available to it. Then gravity complicates the route. General relativity does not abolish the invariant speed. It makes the geometry carrying that speed dynamic. In special relativity, the light cones in an ideal empty region line up in a simple, flat pattern. Add mass and energy, and space-time curves. Clocks at different gravitational potentials no longer keep the same rate. Straightest possible paths bend through the geometry. Light follows those paths even though, in every sufficiently small, freely falling laboratory, it is still measured locally at the same speed. This local word matters. A distant observer using one set of coordinates may assign a different coordinate speed to light moving near a massive body. Radar signals passing close to the sun take slightly longer than a flat space calculation would predict. This is the Shapiro delay. The light has not encountered a patch of vacuum where a local observer watches it crawl below the causal speed. The geometry used to compare separated positions and clocks is curved. Picture hikers drawing a route on a map of a mountain. Each hiker can measure a normal walking speed on the small patch beneath their feet. Yet a distant mapmaker comparing altitude, slope, and horizontal coordinates can describe progress in ways that vary along the route. The map does not change the hiker's local pace. It changes how distant pieces are related. The analogy is imperfect because space-time includes time as part of the geometry, but it protects the key distinction. Local measurement and distant coordinate description are not the same question. Black holes make the distinction unavoidable. Far from a black hole, light can move outward, inward, or sideways. Closer to the event horizon, space-time is curved so strongly that the future directions available to every object tilt inward when drawn in a distant coordinate picture. At the horizon, an outward-aimed light ray still moves locally at the speed of light. It does not hover because its engine fails. The problem is that the future itself no longer includes a path that leads back to the exterior. Inside the horizon, moving toward smaller radius becomes as unavoidable as moving toward tomorrow. A rocket can point outward and fire. A photon can be emitted outward. Both remain inside the future light cone, and that cone leads deeper in. This is another reason the phrase, "nothing can escape," because gravity is faster than light, is wrong. Gravity does not need to reach out from the black hole and pull a departing photon back. The causal paths have been shaped so that departure is no longer among the future options. Changes in gravity also propagate. General relativity predicts gravitational waves, traveling distortions of spacetime produced when masses accelerate asymmetrically. For decades, that prediction remained indirect. Then detectors measured the passing waves, from colliding black holes and neutron stars. On the 17th of August in 2017, the LIGO and Virgo observatories detected gravitational waves from two neutron stars spiraling together in a galaxy roughly 130 million light-years away. About 1.7 seconds later, space telescopes detected a short burst of gamma rays from the same cosmic event. The small difference does not mean the gravitational waves had simply won a race by 1.7 seconds. The gamma rays were probably produced after the merger process reached the conditions needed to launch them, and the exact emission delay is part of the astrophysics. But after crossing roughly 130 million years of travel, the two messengers arrived almost together. That result forced many alternative theories of gravity into a narrow corner. The speed of gravitational waves could differ from the speed of light by no more than a tiny fraction under the conditions tested, at roughly the level of a few parts in 1 quadrillion. Two entirely different messengers had traced the same causal architecture. One was a disturbance of the electromagnetic field. The other was a disturbance of space-time geometry. Their near simultaneous arrival was not proof that every imaginable influence must behave identically, but it was a powerful test of the idea that the invariant speed belongs to the structure of causality itself. Gravity also changes the frequency of light. A photon climbing away from a massive body is measured at a lower frequency by a distant observer. A photon falling inward is measured at a higher frequency. It is tempting to imagine the photon losing or gaining speed. It does not. The relationship between energy, frequency, clocks, and gravitational potential changes while the local vacuum speed remains fixed. The same separation appears in gravitational lensing. A galaxy cluster can bend the paths of light from a more distant galaxy, producing arcs or multiple images. The photons do not slow to turn a corner like a car. They follow the straightest, light-like paths available in curved space-time. So gravity cannot answer where the invariant speed came from. General relativity assumes the same local causal structure and tells us how matter and energy curve it. The theory deepens the role of the speed by making light cones part of a changing geometry. Then ordinary glass appears to contradict everything. Send a pulse through empty space, and it moves at the invariant speed. Send it through water, glass, diamond, or a cloud of cold atoms, and the pulse arrives later. In some laboratories, light has been slowed from hundreds of thousands of kilometers per second to the pace of a moving bicycle. If the speed belongs to space-time, how can matter change it? The answer begins by separating the vacuum limit from the motion of a pulse through a material. Matter contains charged particles. When an electromagnetic wave enters a transparent material, its electric field pushes on electrons bound within atoms and molecules. Those charges respond. Their motion creates additional electromagnetic fields. The original field and the material's response overlap and interfere. The combined disturbance advances differently from a wave in vacuum. It is common to hear that photons are repeatedly absorbed by atoms and then re-emitted after a delay, as though each photon stops at a chain of tiny toll booths. That picture can describe some interactions, but it is not the general mechanism behind ordinary refraction in a transparent material. Random absorption and later emission would scramble direction and timing far more than clear glass does. The useful picture is a coherent light-matter interaction in which the polarization of the material reshapes the advancing wave. The result can be described by a refractive index. An index greater than 1 means the phase of the wave advances through the material more slowly than it would through vacuum. The ratio between the vacuum speed and that phase speed gives the index under simple conditions. Phase is the position of a repeating feature, such as a crest. A light pulse, however, is not one endless perfect wave. It is a group of frequencies combined into a packet. The speed at which the overall envelope moves is called the group velocity. In many ordinary transparent materials, group velocity roughly matches what we mean by the speed of the pulse and is lower than the vacuum speed. Different frequencies interact with matter differently. That is dispersion. It is why a prism can spread white light into colors. The material delays red, green, and blue by slightly different amounts, so they leave in different directions. None of this requires the local causal boundary of vacuum to change. The pulse is no longer a free electromagnetic excitation crossing empty space. It is a coupled disturbance involving the field and the charges in the material. The delay belongs to that interaction. A crowd can make the distinction picturable. An unobstructed runner crosses an empty corridor at a certain pace. Fill the corridor with people who respond to each movement, and a coordinated pattern can move through the crowd more slowly, even if no new law limits the runner's legs. The comparison fails if it suggests photons weave around stationary obstacles. The real process is wave interference and material polarization. But it captures why a composite pattern can have a different speed from the underlying vacuum limit. In 1999, Lene Howe and her colleagues produced one of the most dramatic demonstrations. They cooled a gas of sodium atoms to an extraordinarily low temperature, forming a Bose-Einstein condensate. Under carefully controlled laser illumination, the atoms were prepared so that a narrow range of light could pass through a normally absorbing transition. This effect is called electromagnetically induced transparency. Inside that engineered window, the optical response changed extremely rapidly with frequency. A light pulse was compressed, and its group velocity fell to about 17 meters per second. 17 meters per second is not merely slower than a spacecraft. It is a speed a person can picture beside a road. A pulse that would cross a laboratory in a fraction of a billionth of a second could be made to crawl through the atomic cloud. The experiment did not lower the fundamental speed limit to 17 meters per second. It created a pulse whose energy and information were shared between light and a collective excitation of the atoms. Much of what entered as an optical pulse temporarily lived in the material response. Later experiments could effectively stop and store a light pulse by converting its state into a pattern within the atoms, then recover the optical pulse afterward. The word stop is useful, but it does not mean a free photon sat motionless while remaining an ordinary photon. The excitation was transferred into matter and later converted back. This distinction prevents slow light from becoming evidence against relativity. The causal front of a genuinely new signal cannot be made to outrun the vacuum boundary. Delays, storage, compression, and reshaping all occur inside that limit. Materials also create a situation in which a massive particle can move faster than light, without moving faster than the invariant speed. A charged particle entering water may travel below the vacuum speed of light, but above the phase speed of light in that water. As it passes, it disturbs the electromagnetic polarization of the medium. The responses from successive points can add together along a cone, much as pressure waves from an aircraft moving faster than sound form a shock wave. The optical result is Cherenkov radiation, often seen as a blue glow around nuclear reactors. The particle has not broken the vacuum limit. It has outrun the slower electromagnetic phase pattern available in the material. The comparison with a sonic boom is strong because both involve a source moving faster than waves in a medium. It fails only if the material light speed is mistaken for the causal speed of spacetime. A similar distinction appears whenever scientists report a phase velocity or group velocity above the vacuum speed. The crest of a wave can move faster than the causal boundary. The peak of a reshaped pulse can appear early. A pattern can sweep across a distant surface at an arbitrarily high calculated speed. The question that matters is whether a controllable new piece of information, energy or matter, has crossed between two events outside the light cone. To answer that, physicists use another speed called the front velocity. The front is the very first disturbance that marks where a signal begins. An ideal sharp front requires a broad range of frequencies. Under causal wave propagation, that first genuinely new feature does not outrun the vacuum limit. Group velocity is often an excellent measure of pulse travel. In unusual dispersive media, it can become misleading. The medium may attenuate the back of a pulse and amplify or preserve the front, shifting the peak forward. A detector can then register the peak sooner than expected, even though no new information has traveled superluminally. Think of a long line of falling dominoes viewed through a moving window that hides some tiles and reveals others. The brightest visible cluster might seem to jump forward because the pattern has been reshaped, not because any domino passed through its neighbors. The analogy is only a guide. Optical reshaping occurs through interference and gain or absorption, not through a literal window. The key is that a peak is a feature of a waveform, not necessarily a tagged object carrying a message. Experiments with fast light media have produced group velocities greater than the vacuum speed and even negative group velocities, where a pulse peak can appear to leave before the incoming peak reaches the far side. These results sound like time reversal until the full waveform is examined. The output is assembled from the early leading portion of the input through the known response of the medium. A genuinely unpredictable change does not emerge before causal contact. Light can therefore be slower than the speed of light, faster than the speed of light, and exactly at the speed of light, depending on which light, which medium, and which definition of speed is being used. Only one of those phrases names the invariant boundary. The cleanest way to see the difference is to make something that can move faster than light, without containing anything that moves from one end to the other. Aim a laser at the moon and sweep the beam across its surface. The moon is far enough away that a small turn of the laser can move the illuminated spot across thousands of kilometers. Turn quickly enough and the calculated speed of the spot can exceed the speed of light. No object skims across the lunar ground. Photons reaching one location were emitted in a different direction from photons reaching the next. The first spot cannot send a message to the second by moving along the surface. Each location receives its own light from the source. A shadow can behave the same way. Move a blocker near a lamp, and the edge of the shadow can sweep across a distant screen faster than light. Darkness has not become a substance carrying information sideways. The pattern records where separate rays were blocked. Two blades of a pair of scissors provide an even simpler geometry. Close, very long blades, and the mathematical point where their edges cross, can move faster than either blade. That crossing point is not a particle. Nothing material has to follow it. Patterns are allowed to ignore the speed limit when their apparent motion does not connect neighboring points through a physical influence. In March of 2026, an experiment published in Nature brought this distinction into an unusually vivid form. Researchers studied optical phase singularities, points in a wave field where the amplitude falls to zero and the phase becomes undefined. Around such a point, the phase can wind like a vortex. These dark points can be tracked through space and time as patterns in a changing wave field. They can appear in pairs, move, and annihilate. Near the moment when two singularities meet and disappear, the location of the zeros can accelerate dramatically. Theory had predicted that their apparent velocities could become unbounded in the ideal mathematical limit. The researchers used ultra-fast electron microscopy to map the dynamics of optical singularities in thin membranes of hexagonal boron nitride. Their measurements revealed apparent velocities exceeding the speed of light as singularities approached annihilation. The result is real. The phrase superluminal is not a journalistic invention attached afterward. The measured pattern velocities exceeded the relevant light speed and, in the reported description, could exceed the vacuum speed, yet no photon, atom, energy packet, or controllable message was carried from one singularity position to the next at that apparent velocity. A phase singularity is a zero in a field pattern. Its motion is determined by how the surrounding waves change together. Near annihilation, a small change in the field can move the calculated zero by a large distance. Imagine two nearly matching sound waves creating a point of silence in a room. Change their relative phase, and the silent point may leap across the space. The air at the first quiet point did not travel to the second. The zero moved because the entire interference pattern changed. The optical experiment is far more intricate, and the singularities possess topological structure that the simple sound picture does not capture. But the causal lesson is the same. A location defined by cancellation can move differently from the things whose cancellation defines it. This is why the speed limit has never meant that every number obtained by dividing a distance by a time must remain below the speed of light. It means that local matter, energy, and usable influence cannot be sent outside the causal cone. Astronomy produces another famous superluminal illusion. A jet launched near a black hole can point almost toward Earth while moving close to the speed of light. The jet advances toward us as it moves sideways across our view. Light emitted later has less distance to travel, so the interval between observed positions is compressed. The apparent transverse motion can exceed the speed of light even though the plasma remains below it. The effect is called apparent superluminal motion. It once seemed capable of threatening relativity. Instead, its geometry became evidence that the jets were genuinely moving at relativistic speeds and aimed close to our line of sight. Every supposed escape, therefore, demands the same questions. What exactly is moving? Relative to which frame? Is the reported quantity a phase, a group, a peak, a projection, a coordinate, a correlation, or a material carrier? Can an unpredictable message be attached to it and recovered outside the light cone? Most faster-than-light headlines collapse under those questions. Some reveal errors. Others reveal beautiful physics that relativity permits. One category refuses to collapse so easily because it challenges a different intuition. Quantum entanglement produces correlations between distant measurements that cannot be explained by giving each particle a complete local instruction list in advance. Bell experiments have tested this repeatedly. In a loophole-free test reported in 2015, entangled electron spins in diamond were measured in laboratories separated by more than a kilometer. The correlations violated the bound imposed by local realist models under the tested assumptions. The result is not merely that the particles happen to match. Their statistical relationship is stronger and more structured than any local hidden set of predetermined answers can reproduce. It is tempting to say that one particle instantly tells the other what result to choose. That wording creates a messenger the experiment does not reveal. Each local measurement result is individually random. The observer on one side cannot choose the outcome. Changing the measurement setting changes the pattern that appears when the two sides later compare their data, but it does not create a controllable local signal on the distant side. Before ordinary communication brings the records together, neither observer can extract a message from the random sequence alone. Entanglement is non-local in a precise quantum sense. It defeats a classical picture in which distant systems carry independent local properties that determine every possible measurement result. But quantum theory also obeys no signaling. The correlations do not provide a telegraph outside the light cone. That combination remains conceptually unsettling. Reality does not decompose into the local hidden pieces that classical intuition expects, yet operational causality survives. Experiments have tested both the Bell correlations and the absence of usable faster-than-light signaling. Nature can be more connected than local classical stories allow, without becoming a machine for sending tomorrow's answer into yesterday. The invariant speed does not demand that every physical relationship be local in the naive sense. It demands that controllable cause and effect respect the cone. The largest apparent challenge comes not from a laboratory, but from the expansion of the universe. Distant galaxies can have recession rates greater than the speed of light. Some galaxies whose ancient light reaches us today have been receding superluminally according to the standard cosmological description. This is not a loophole hidden in an exotic theory. It follows from general relativity applied to an expanding universe. The statement sounds forbidden because recession is described with a velocity. But the cosmic recession rate is not the local speed of one galaxy passing another through the same inertial frame. It is the rate at which the large-scale distance between widely separated co-moving locations changes as the geometry evolves. Special relativity limits local motion through space-time. General relativity allows the relationship between distant regions of space-time to change. A grid drawn on an inflating sheet is a common analogy. Points on the sheet separate, even if each point remains locally at rest with respect to the nearby material. The analogy helps with expansion, but the universe is not an elastic sheet growing into an outside room. The grid itself represents changing distances within the geometry. At every local point, a freely falling observer still measures a passing light beam at the invariant speed. No galaxy overtakes a nearby photon in its own local frame. The superluminal recession appears only when a cosmological model compares far separated regions using a shared cosmic time and a changing distance convention. There is a distance called the Hubble radius at which the recession rate equals the speed of light at a given cosmic time. It is tempting to call that surface the edge of the observable universe. It is not. A photon moving toward us from beyond the Hubble radius can initially find its proper distance from us, increasing because the intervening space expands faster than the photon reduces the distance locally. As the expansion rate changes, the Hubble radius can grow past the photon. The photon then begins making net progress toward us and may eventually arrive. That is why we can observe light from objects whose recession was greater than light speed when the light was emitted, and can observe some objects that are described as receding faster than light now. The true limits depend on horizons, not simply on the current Hubble radius. The particle horizon marks the farthest distance from which light has had time to reach us since the early universe. The cosmic event horizon marks a different boundary. It separates events that can ever send us a signal in the infinite future from events whose future light will never reach us if the current accelerated expansion continues. Some galaxies visible today will eventually pass beyond our ability to receive newly emitted signals. We will continue to receive older and increasingly redshifted light for a time, but no message sent after a certain cosmic moment can cross the expanding distance to us. The speed of light has not been defeated. It has been made consequential on the scale of the entire universe. A finite causal speed combined with cosmic expansion creates regions that can share a past but not a future conversation. Early universe inflation pushes the idea further. During inflation, distances between co-moving points grew extremely rapidly, and widely separated regions could recede from one another faster than light. Again, nothing had to race locally through space beyond the causal speed. The geometry expanded. Inflation is invoked partly because regions now far apart appear to have originated from a much smaller causally connected domain before being driven apart. The theory does not use faster-than-light signaling to solve the horizon problem. It changes which regions were once close enough to communicate before the rapid expansion. This distinction between motion through space and changing spatial geometry is easy to say and difficult to picture. The safest anchor is always local measurement. Build a small, freely falling laboratory beside any ordinary galaxy or photon, and the local light cone retains the same form. Compare huge distances across an evolving cosmos, and recession rates can exceed the number associated with that local cone without allowing a nearby object to outrun light. The speed limit is local. Causality is global, only after the geometry is known. That sentence also explains why proposed shortcuts, such as wormholes and warp geometries, receive serious mathematical study without becoming established faster than light technology. General relativity contains space-time arrangements in which a traveler could connect distant regions without locally crossing the light cone. But constructing and stabilizing those arrangements appears to require exotic conditions, and no evidence shows that nature permits a usable version. The equations can describe a route. That is not the same as the universe providing the road material. Until evidence says otherwise, the causal structure tested in laboratories, particles, light, gravity, and astronomy remains intact. The most famous modern challenge did not begin with a galaxy, a quantum correlation, or a wave pattern. It began with a cable and a clock. In September of 2011, the OPERA experiment reported that neutrinos sent from CERN in Switzerland to the Gran Sasso laboratory in Italy appeared to arrive about 60 billionths of a second earlier than light would have crossed the same baseline. The distance was more than 730 kilometers. 60 billionths of a second sounds negligible. In a race against light, it was enormous. The reported early arrival implied that the neutrinos had exceeded the vacuum speed by roughly 20 parts in a million. The collaboration did not announce a new theory as settled fact. It released the result for scrutiny after extensive internal checks. The measurement triggered excitement because neutrinos were already unusual particles. They interact weakly with matter, pass through Earth, possess tiny masses, and change among three flavors. If any known particle were going to reveal a subtle crack in established physics, neutrinos seemed capable of delivering it. But a result does not become true merely because it would be revolutionary. Other experiments and astronomical observations already pressed hard against the claim. Neutrinos from supernova 1987A had arrived within hours of the light, after traveling for roughly 168,000 years. The emission processes were not simultaneous enough to produce a laboratory precision test, but the observation left little room for the kind of large, simple speed excess OPERA seemed to report across all energies and conditions. The timing system was examined again. A fiber optic connection carrying timing information was found to be improperly connected, creating a delay that made the neutrinos appear early. A separate issue involving an oscillator pushed the timing in another direction. Once the apparatus was corrected and new measurements were made, the superluminal result disappeared. Independent experiments at Gran Sasso also measured neutrino speeds consistent with the speed of light. The episode is sometimes told as embarrassment. It is more useful as a portrait of how a speed limit is tested. The collaboration measured a baseline through Earth with geodesy. It linked clocks, separated by hundreds of kilometers. It accounted for Earth's rotation. It modeled the production time of particles that could not be tracked as individual travelers from source to detector. A fault smaller than a fingertip altered an inference about the foundations of space-time. That does not mean foundational tests are hopeless. It means extraordinary precision turns ordinary hardware into part of the theory test. A connector, an oscillator, a survey marker, and a timing calibration can become the difference between new physics and an error. The response also shows why relativity is not protected by loyalty. Physicists published hundreds of papers exploring what a superluminal neutrino would imply. Other teams prepared independent measurements. The claim was not rejected because Einstein was famous. It was rejected because the corrected experiment and later evidence did not reproduce it. A real violation would need to survive exactly that process. This is the standard applied to modern searches for energy-dependent light speed, directional differences, massive photons, unusual neutrino propagation, or quantum gravity effects. A small deviation must remain after source physics, material delays, detector response, clock synchronization, gravitational geometry, and every known systematic effect are accounted for. So far, the invariant speed has won those confrontations. Even measuring it contains a subtle problem. A round trip is straightforward. Send light from one clock to a mirror and back to the same clock. One instrument records departure and return. Divide the total distance by the elapsed time. A one-way measurement is different. It needs one clock at the start and another at the destination. Before the light is sent, those separated clocks must be synchronized. But synchronizing them by exchanging signals already requires a rule about how long the signals take in each direction. In special relativity, the usual Einstein synchronization convention assigns equal one-way travel times in opposite directions for light in an inertial frame. With that convention, the one-way speed is the invariant value. Experiments test the full network of predictions with enormous precision, but the bare one-way value cannot be separated from the synchronization convention in the same simple manner as the round-trip speed. This does not make relativity arbitrary. Different synchronization conventions change coordinate labels, not measurable causal outcomes. Round-trip light speed, time dilation, particle dynamics, electromagnetic behavior, and every closed experimental comparison remain constrained. The convention is about how distant clocks define simultaneous, not about whether a message can beat a causal loop. Once again, the difficulty lives in the word now. A useful thought experiment shows how completely the limit reaches beyond light. Imagine that the sun could vanish without warning. Real physics does not provide a process that simply deletes its mass and energy, so this is only a device for asking how changes propagate. Earth is about 8 light minutes from the sun. The last sunlight already in flight would continue arriving during that interval. General relativity says the change in the gravitational field would also propagate outward rather than updating the solar system instantly. Earth would continue along its existing path until the new gravitational information arrived. The story corrects a Newtonian instinct. In Newtonian gravity, a change in one mass can affect another at once, across any distance. In general relativity, gravity is not an invisible pull transmitted through an unmoving stage. It is the geometry of space-time, and changes in that geometry propagate at the causal speed. This does not mean ordinary planetary gravity is delayed in the naive way that would make Earth chase the sun's old position. The gravitational field of a steadily moving source includes velocity-dependent structure, and the full relativistic interaction preserves stable orbits. The simple vanished sun picture concerns a genuine change in the source, not a constant lagging image of where the source used to be. Electromagnetism has a similar feature. A charged particle that begins to accelerate does not make the entire universe update its electric field at once. The change propagates outward. Far away, an observer continues to encounter the older field until the new disturbance arrives. Electromagnetic radiation is part of that traveling update. Fields therefore carry history locally. At any point, the field contains information that has had enough time to arrive from its past light cone. The universe does not maintain one central ledger and revise every location simultaneously. Each region can respond only to what has reached it. This gives the finite speed a constructive role. It does not merely forbid travel, it allows physical laws to be local. A field at one event evolves from nearby conditions, and influence spreads through connected events rather than leaping across the cosmos. The light cone is the bookkeeping system that makes that local evolution compatible from one observer to another. An infinite causal speed would require a radically different structure. Distant changes could be felt with no travel time, and the relativity of simultaneity could not play its present role. The actual universe, instead, builds every long-distance interaction from local propagation. The invariant speed has become so reliable that modern civilization quietly uses it as a measuring tool. Radar sends a radio pulse toward an object and records the return. The time delay becomes distance. Laser ranging does the same with shorter wavelengths and exquisite precision. Pulses sent to reflectors left on the moon return after roughly 2.5 seconds, allowing the Earth-Moon distance to be tracked to extraordinary accuracy. The meter itself is now defined by light travel. The second is defined through a specific atomic transition in cesium. Once the duration of the second is fixed, the exact value assigned to the speed of light fixes the meter. A length laboratory realizes the unit through frequency, wavelength, and interferometry, rather than preserving one physical bar as the ultimate ruler. This is the reversal introduced at the beginning. The speed was once an unknown, found by measuring distance and time. It became stable enough that distance is now found through the speed and time. Satellite navigation depends on the same structure. A receiver determines its position by comparing precisely timed signals from several satellites. Light travels about 30 centimeters in 1/1000th of a second. A timing error too small for a human nervous system to notice becomes a meaningful position error. The clocks on navigation satellites also move relative to clocks on Earth and sit in a different gravitational potential. Special relativity makes motion slow them relative to Earth-based clocks. General relativity makes the weaker gravity at orbital altitude speed them up by a larger amount. The system must account for both effects. Without those corrections, position errors would accumulate rapidly. The receiver in a pocket is therefore solving a practical space-time problem. It identifies where the intersections of several expanding light signals meet its clock. Global communication also lives below the limit. A signal in optical fiber usually propagates at roughly 2/3 of the vacuum speed because of the material's refractive index. Data crossing an ocean must pay that delay before routers, servers, and software add their own. Financial markets build facilities near exchanges because even fractions of a millisecond matter. No faster processor can remove the minimum travel time between separated places. On a computer chip, electrical changes propagate through conductors and insulating structures at a significant fraction of the vacuum speed, not instantaneously. As components shrink and clock rates rise, the time required for signals to cross the chip becomes part of the design. Engineers cannot treat every distant transistor as though it learns the new state at once. The limit becomes unmistakable beyond Earth. Light takes a little more than 1 second to travel from the moon to Earth. A conversation across that distance would contain a pause of more than 2 seconds for a reply, even if every machine responded instantly. Sunlight reaches Earth after about 8 minutes and 20 seconds. We see the sun not as it is now, but as it was when the light left. The one-way delay between Earth and Mars changes greatly as the planets orbit, ranging from a few minutes to more than 20 minutes. A rover cannot be driven like a remote-controlled car. Engineers send instructions, wait for them to arrive, and later receive the result. The machine needs enough autonomy to avoid a rock or halt when conditions differ from the plan. At the outer planets, the delay grows to hours. A command can spend a large part of a working day crossing the solar system before the spacecraft even begins to act. The response must cross the same distance back. The speed of light is enormous inside a room and painfully slow across a planetary system. Across the galaxy, it becomes a barrier to community. A message to the nearest star system needs more than 4 years one way. A reply cannot arrive in less than roughly 9 years after the first transmission, even before anyone takes time to think. Across the Milky Way, a conversation can span tens of thousands of years. This consequence changes the meaning of extraterrestrial detection. A radio signal from a civilization 1,000 light-years away would show what that civilization transmitted 1,000 years ago. Any reply would reach their region another 1,000 years later. Detection would not create immediate contact. It would connect histories. Astronomy is built from those delayed histories. The moon is seen a little over a second ago. The sun is seen minutes ago. Nearby stars are seen years ago. The Andromeda Galaxy is seen more than 2 million years ago. The cosmic microwave background carries an image from the young universe more than 13 billion years into the past. A telescope does not look through distance alone. It looks down a light cone. That is why the finite speed is not merely an inconvenience. Without travel time, the sky would have no layered record. Every visible object would present one universal instant, if such an instant could even be defined. Because signals take time, distance stores history. The same constant appears in the relationship between mass and energy. In Einstein's famous equation, mass is multiplied by the speed of light squared to obtain an equivalent energy. The enormous conversion factor explains why a small amount of mass can correspond to a vast amount of energy. The equation is sometimes described as though matter contains compressed light. That is not generally correct. The constant appears because mass and energy are parts of one relativistic structure. The invariant speed converts the units and sets the scale of their relationship. Particle accelerators expose the relationship directly. As a proton receives more energy, its momentum continues to increase, while its speed approaches the invariant limit ever more slowly. The machine does not run out of the ability to add energy. It runs into a geometry where additional energy no longer produces the Newtonian increase in speed. The energy can instead create new particles, increase momentum, or transform in collisions. The boundary redirects what acceleration can accomplish. Every use returns to the same model. The speed of light is not simply how rapidly illumination spreads. It is the constant that connects clocks to rulers, mass to energy, local motion to causality, and distance to history. Now return once more to the flashlight on the moving spacecraft. The beam does not inherit the ship's speed because there is no universal space and universal time in which the two velocities can be added in the Newtonian way. Earth and the spacecraft divide spacetime differently. They disagree about elapsed time, measured distance, and which separated events happen together. Those disagreements are not adjustments painted onto reality after the experiment. They are the relationships that allow both observers to describe the same causal geometry. The electromagnetic field respects that geometry. Maxwell's equations contain waves that propagate at the invariant speed. The quantum electromagnetic field contains massless excitations, photons, whose free paths lie on the light cone. General relativity preserves the same local cone while allowing matter and energy to curve its orientation from place to place. Gravitational waves trace it as well. These are not competing answers. They are layers. Maxwell tells us why light has a definite wave speed in classical electromagnetism. Special relativity tells us why that speed is the same for inertial observers, and why massive objects cannot reach it. Quantum field theory tells us why a massless photon travels on the causal boundary rather than below it. General relativity tells us how that boundary behaves when spacetime is curved. None tells us why existence had to choose a Lorentzian causal structure with a finite invariant speed. That is the honest frontier. Some approaches to quantum gravity ask whether spacetime is fundamental or emerges from more basic relationships. In an emergent picture, Lorentz symmetry might arise at accessible energies the way a simple wave speed emerges in a material, while tiny deviations appear near a far more extreme scale. Other approaches treat the symmetry as exact. Experiments search for directional changes, energy-dependent delays, forbidden particle reactions, or other traces of a deeper structure. No confirmed deviation has replaced relativity. The question also needs protection from the decimal number. Why is the speed exactly 299,792,458 meters per second? Because a meter and a second are human units. That number is not a pure fingerprint of the universe. Express the same speed in kilometers per second, and the number changes. Express time in years and distance in light years, and the number becomes 1. Since 1983, the meter has been defined so the value in meters per second is exact. The deeper physical content lies in relationships that do not depend on the choice of units. Ratios of speeds are meaningful. So are dimensionless combinations of fundamental constants. A claim that a dimensional constant has changed must ultimately be translated into a change in some measurable dimensionless relationship or into a clearly specified system of standards. This does not make the invariant speed conventional. Choosing the label on a ruler does not choose whether high-energy particles obey relativistic dynamics, whether clocks dilate, whether gravitational waves share the causal cone, or whether a message can return before it was sent. Units choose the number. Nature chooses the relationships. Could those relationships be different elsewhere or at another time? Scientists have tested light from distant astronomical sources across wide ranges of energy, compared precision clocks as Earth moves and rotates, examined the behavior of particles at accelerators, measured gravitational waves, and searched for Lorentz violation. These tests cover an enormous territory, but no finite collection of experiments can prove a law for every energy, place, and era. The strongest truthful statement is not that breaking the invariant speed is logically impossible under every imaginable future theory. It is that every established local theory of matter and gravity is built around the causal limit, and every confirmed observation so far is consistent with it within the tested precision. A genuine exception would not be a faster rocket. It would require a revision of the architecture connecting space, time, energy, and cause. That is why apparent exceptions are so instructive. Light can move slowly through a material because the traveling disturbance includes matter. A charged particle can outrun light in water because the material phase speed is below the vacuum limit. A wave peak can appear superluminal because the waveform is reshaped. A laser spot, shadow, crossing point, or optical singularity can sweep faster than light because no object or message travels along the pattern. Entanglement can create non-classical correlations without providing a controllable signal. Distant galaxies can recede faster than light because the geometry between them changes without local motion through the cone. Each case preserves the limit by revealing what the limit actually applies to. The rule is not that the universe bans every superluminal-looking quantity. The rule is that a physical influence cannot locally carry usable cause and effect outside the light cone. This is also why the speed of light feels so different from ordinary limits. The speed of sound can be exceeded. The speed of a wave on water can be exceeded. Those speeds belong to states of matter, and a sufficiently fast object can form a shock wave through the medium. The vacuum causal speed is not a traffic rule imposed on objects moving through a hidden substance. It defines the distinction between the kinds of paths that massive objects, massless fields, and causal signals can have. A runner can break a record because the track remains the same. Breaking the invariant speed would mean changing what counts as a track, a clock, and an order of events. The discovery, therefore, began with the wrong question in a productive form. Humanity asked how fast light crosses space. Rømer used a moon of Jupiter to show that the crossing takes time. Fizeau caught the delay between teeth of a turning wheel. Maxwell found the same speed hiding inside electricity and magnetism. Michelson and Morley searched for the medium that should own it, and found no expected wind. Einstein kept the speed and allowed space and time to change instead. The number survived because it was never only a number. It tells a spacecraft how its clock relates to Earth's clock. It tells an accelerator why energy stops producing ordinary increases in speed. It tells a black hole which future directions remain open. It tells a telescope how far into history each image reaches. It tells a navigation receiver where several timed signals meet. It tells a civilization how long a question must travel before another world can answer. Most of all, it tells the universe which events can belong to the same chain of cause and effect. Switch on the moving flashlight one last time. Earth sees the ship cross the sky. The crew sees Earth slide backward. Both see the pulse leave the lamp at the same invariant speed. Neither measurement is rescued by a secret force acting on the photon. The agreement is created by the fact that their distances and times are not universal pieces waiting to be compared. They are frame-dependent parts of one space-time structure. The light does not adjust itself to each observer. Each observer's space and time fit the same light cone. That is what the speed of light really is. It is the visible edge of causality, expressed as a speed because human beings first met it by timing a beam. Light gets that speed because a massless electromagnetic excitation has no slower path through vacuum. Nothing massive can reach it, because massive paths remain inside the cone. No usable signal can pass it, because outside the cone, cause and effect lose a consistent order. And the final Y remains open at exactly the point where physics reaches bedrock. We know the symmetry, we know the geometry, we know the fields that obey it. We know how fiercely experiments have tested it. We do not yet know whether that structure is ultimate, or whether some deeper theory will explain why it exists. The uncertainty does not weaken the answer already earned. Light was the messenger that exposed the rule. The rule belongs to the universe.